All right, let's dive right in. Today, we're looking at a brand new AI architecture that fixes a really catastrophic memory flaw in pretty much all of today's models. But here's the thing, it doesn't just put a band-aid on the problem. No, it performs surgery. It removes the very part of the process that causes the issue in the first place. And what we're left with is a totally new and frankly better way for an AI to think. So let me just ask you this. What if your AI had a perfect memory? I mean, a truly perfect, unerasable one that could recall every single connection between every piece of data you've ever given it, and do it instantly. Now, that might sound like science fiction, but it's actually the goal of this new architecture. It's designed to fix a critical failure that causes even our most powerful, most advanced AIs to just completely fall apart when they're faced with genuinely complex problems. Okay, so to really get why this new solution is such a big deal, we first need to understand the problem. And trust me, it's a huge one. It's this hidden memory crisis that's right at the heart of modern AI. And it's the reason why even the smartest models out there eventually fail. Now, standard retrieval-augmented generation, or RAG, is awesome for simple stuff. You ask a basic question, it finds a single document with the answer. Easy. But what happens when the answer isn't in one place? What if it's spread across many connected documents? Well, early attempts, like this graph chain of thought, try to make the AI walk through that web of data. The problem? It gets lost. Badly. You see, the fundamental flaw is asking a large language model to navigate a knowledge graph in the first place. LLMs are probabilistic. At their core, they are just incredibly sophisticated guessing machines. So when you ask one to follow a path, it isn't reading a map. It's just predicting the next turn based on what seems most likely. This leads to what's called pathfinding hallucinations, and it creates an absolutely catastrophic problem. And this is where things go completely off the rails. It kicks off this disastrous feedback loop. With every single step the LLM takes, it has to explain its reasoning. And that reasoning gets added back into the prompt. The prompt gets bigger and bigger and bigger. This inflates the GPU's working memory, the KV cache, which just balloons uncontrollably until, boom, it hits its physical limit. The whole system either crashes, or even worse, it starts silently throwing away crucial information to save itself. And get this, the scale of this problem is just staggering. To process just one single large prompt on a big 70 billion parameter model, you might need 40 gigabytes of the most expensive memory on the entire planet, just for that KV cache. It's a completely unsustainable physical and economic bottleneck. So how do you solve an impossible memory problem like that? Well, the answer is you don't. You bypass it. You create an architectural workaround that completely changes the AI's job description. You demote the LLM from this clumsy guessing pathfinder into a highly focused synthesizer of information. This quote from the source material really says it all. Instead of trying to give the AI a bigger and bigger memory so it can walk the graph, you just take that job away from it entirely. You strip it of all its retrieval duties, and you let a strict, cold, hard mathematical pipeline take over instead. And the heart of this new architecture is called the three-manifold mind. You should think of it as this super disciplined, purely mathematical engine that completely takes over the job of finding and organizing all the evidence. And the best part? It does all the heavy lifting in standard, abundant, and cheap CPU memory, which totally replaces the LLM's unreliable and expensive guesswork. Okay, so let's pop the hood and really break down how this thing works. The system is made of three distinct components, or minds. The best way to think about them is as three different specialists, all working together on a perfectly seamless and totally deterministic assembly line. First step, we've got Mind 1, the librarian. This is the system's long-term memory. It holds everything, all of your knowledge, inside a neat, portable cartridge. The raw text itself, that lives in a simple SQLite database. The actual meaning of that text, its semantic concepts, are stored as mathematical vectors in a phase indexed, which lets us do ultra-fast searches. And finally, all the relationships, the knowledge graph itself, is mapped out perfectly using Network X. Next is Mind 2, the researcher. The moment a query comes in, this mind just springs into action. First, it does what's called anchor discovery, using that super fast FISIS index to find the most relevant starting points. Then, instead of looking at the whole library, it just carves out a small, temporary, query-specific graph in CPU RAM. It's called a session seam. This is so smart because it avoids wasting time on anything that's not relevant to the question you're asking right now. And finally, we have Mind 3, the analyst. Think of this one as the dispassionate judge. It takes that temporary graph from the researcher and mathematically scores every single piece of evidence based on its importance. Then, it does something called a token-constrained max heap extraction, which is a fancy way of saying it's like perfectly packing a suitcase. It just greedily grabs the highest scoring items one by one until the LLM's context window is filled to the absolute brim, with zero wasted space. Okay, so you're probably wondering, how does the analyst actually decide what's important? This isn't some black box magic. It's pure, transparent math that perfectly fuses two very different types of information: semantic relevance, what something means, and structural importance, how it connects to everything else. Here's the core challenge. Semantic relevance scores from cosine similarity are pretty big numbers, like 0.92. But structural importance from PageRank gives you these tiny, tiny fractions, like 0.085. You can't just add them together. It's like adding feet and ounces. The scales are all wrong. So the solution is something called min-max normalization, which brilliantly rescales both sets of scores to a simple 0 to 1 range, putting them on an equal playing field so they can be compared fairly. And once those scores are normalized, they get fused together using this incredibly simple but really powerful gravity score. G is the final score for any piece of data, S is its structural importance, T is its semantic relevance, and here is where the magic really happens, with those little alpha and beta weights. This is where you get real, fine-tuned control. By tuning these alpha and beta knobs, you're essentially changing the lens of the system. So if you need to understand complex relationships, like how does component X impact system Y, you crank up alpha to create a structural lens, prioritizing the central hubs and connecting pieces. But if you just need to find one specific fact, like a clause in a contract, you crank up beta for a semantic lens, prioritizing the exact keyword matches. You get to decide what matters most. And here is a killer detail. To make sure this system is truly 100% deterministic, it has a simple rule for breaking ties. If two pieces of evidence end up with the exact same gravity score, it just sorts them by their unique ID number. It sounds like a small thing, but this is what guarantees perfect bite-for-bite reproducibility on every single run. No randomness, ever. And what's really brilliant is that because this whole process is pure math, the system can basically self-diagnose. It has a built-in friction detector that spots problems before it wastes time and money sending junk to the LLM. For instance, it can detect an island effect. That's when a piece of data sounds really relevant but has zero connections to anything else in the graph. That's a huge red flag for a potential hallucination. It can also spot a gravity collapse, where all the scores are flat, which tells you the evidence is probably contradictory, or maybe you just asked a bad question. So let's step back from the deep technical details for a second and talk about the real-world payoff. Because this isn't just a cool science project. It's an absolute game changer in terms of performance, cost, and maybe most importantly, accessibility. By taking the LLM completely out of the loop for finding the data, this architecture achieves up to a 90% reduction in both how long it takes and how much it costs. Complex reasoning that used to take tens of seconds and a bunch of money now happens in milliseconds for fractions of a penny. And this leads to something that I think is incredibly important: a hardware and economic rescue. Since all the heavy lifting happens in cheap CPU RAM, you don't need a massive, expensive data center GPU anymore. You can now do enterprise-scale, complex, multi-hop reasoning on a small local model that's running on a consumer graphics card with just 8 gigs of VRAM. This puts a level of AI reasoning that was once only available to massive corporations into the hands of pretty much everyone. And of course, the work is never done. The future roadmap is all about making this system even more robust for the real world. That means tackling things like temporal drift, so that old, stale data doesn't unfairly dominate the results. It means solving schema mismatch, so the system understands that CEO Smith and J. Smith are the same person. And crucially, it means building in hardwall security to guarantee that one user's data can never, ever leak into another's. You know, all of this really points to a new direction for AI development. The future isn't just about a race to build bigger and bigger models, a bigger brain. It's about designing smarter, more efficient architectures, a better nervous system. And that leaves us with a really fascinating question to think about. What's the next critical bottleneck in AI that we should bypass?